This conference will now be recorded.
Good morning, one and all. Yesterday we have discussed the syllabus of probability theory and stochastic process. Now today we are going to start our first lecture of first unit. We'll see. And for studying a probability theory, we need to have some idea about set theory. That means we need to analyze sets. In case of probability theory, we have got our syllabus is probability introduced through sets and relative frequency. This is your first topic. Sets are important for analyzing your probability. Based on set theory only, we are going to explain the probability concepts. This is the first topic of your probability theory and stochastic process, first unit. So now we'll try to have definitions of all these things: set, countable and uncountable set, empty set or null set, finite set, infinite set, subset, and universal set. We'll see the definitions of these things. First, we'll see the definition of set. Set. A set is a collection of objects or elements. That means when you perform an experiment, the outcomes of the experiment group together to form a set. If you go for an example, I'll give an example. Before that, a set is represented with a capital letter and an element with a small letter. Example, if B is an element of set X, then B belongs to X such that X is having an element B in case of this X set. When you go with countable and uncountable sets, a set is said to be countable set if the elements can be put in one-to-one correspondence with the natural numbers, else it is said to be uncountable set. That means when you are going to assign a number for the outcome, or one-to-one correspondence is maintained with the natural numbers, then it is called a countable set, else it is not. It is an uncountable set. Let A equals X. Let A equals a set containing X, where X is going to vary between 0.5 to 8.5. Since X is not a natural number, between these two, it can have 10 values, 100 values, or 200 values, or infinite number of values that we cannot expect. So this is called as an uncountable set. Similarly here, let A is equals to X, where X is having a values between 0.5 and 8.5. So X is a natural number. In the sense, X are natural numbers. If they are natural numbers, the values between these two are 1, 2, 3, 4, 5, 6, 7, and 8, and the remaining are not there. Here we can count the values. So this is called as an countable set. Now we go with an null or empty or void set. Now a set that does not contain any elements is called the empty or null or void set. The symbol used to represent an empty set is either set with no elements or a phi symbol. These two symbols are used for representing an empty or null or void set. Let A equals X, 9 less than X less than 10, and X is a natural number. Here in between of these two, you don't have any natural number, 9 and 10, between 9 and 10. So we call this as an null set. Let W equals D, D is greater than 8. D is a number of days in a week. D is a number of days in a week. Here we have got the number of days in a week to be only 7. If D is greater than 8, there is no week number greater than 7. So this is also an empty set or null set or void set. And finite and infinite sets. A set which is empty or contains a definite or countable number of elements is called a finite set. If a set is having finite number of elements, that means you have got finite element, then we call it as a finite set. That is, we need there must be an element which is countable. Sets defined otherwise for uncountable or indefinite numbers of elements are referred to as infinite sets. That means a set containing a limited number of elements is called as an finite set. That means it may be an empty set or a set with some numbers. If you have got infinite number of elements, then we call it as an infinite set. Example, we can have here 1, 2, 3. We can call this as a set. If I give this thing dot 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 dot, that means it is going to vary. It is going to move in this direction up to infinite. Then this is called as an infinite set. Now, A equals AEIOU is a finite set because it represents the vowel letters in the English alphabet series. Right? Here AEIOU got only 5 letters. We can count them and we can assign natural numbers, and it is called a set which contains vowels, which is finite. Similarly, if you go with this set D, X is a number appearing on a die roll, is an finite set because it contains 1, 2, 3, 4, 5, 6 elements only. We have got only 5 appearances when you roll a die. When we roll a die, we have got only 5. Here, C is a set which is having P. P is a prime number. It is an infinite set. P is a prime number. There are infinite number of prime numbers. In infinite number of prime numbers. Similarly, K. K is a real number. It is also an infinite. So we have got the real numbers placed to be infinite. If you give a natural numbers K is a natural number. In that case also it varies to infinite, and we call it as an infinite set, universal set. A universal set contains all the elements of the problem under consideration. It is generally represented by the letter U. The set of real numbers is a universal set for all natural, whole, odd, even, rational and irrational numbers. Real numbers contains all these things, and we call this real number set as an universal set. Two sets A and B are called disjoint or mutually exclusive if they have no common elements. If they have got no common elements. As an example, we can see this. A is a set where when you roll a die, you'll get an odd number. That is 1, 3, and 5. And B is a set where you roll a die and you see an even number, 2, 4, and 6. Now, when you look into these things, you don't have any common elements between these two. So these two sets are called disjoint or mutually exclusive sets. We call these two sets as mutually exclusive sets. Example A, an odd number, and B, an even number. When you look into these two things, they are both disjoint sets or mutually exclusive set. Now, A is a subset of S. So it is represented with this symbol. A is a subset of S and is called as an event. A is called, and it is called as an event. The term outcome and event reflects the fact that we are describing things that may happen in real life. But when you go with when we deal with mathematics or mathematically, these are described as elements and subsets of a sample space. Outcome is represented as element, event as a subset, and sample space with an experiment. Now, example, if we roll a die and observe the number, two possible events are that we get an odd outcome and that we get at least 4. We get at least 4. If we view these as subsets of a sample space, A is having odd number 1, 3, and 5, and another experiment B is another event is having B 4, 5, and 6. At least 4, in the sense you may get 4, 5, or 6. Now, when you look into this, A is an odd outcome and B is an at least 4. Now, in this case, these both are not disjoint sets. They are not mutually exclusive. Why? Because element 5 is common between these two. Now we'll see a few examples and we define whether it is finite, infinite, countable, or these things. First, set A. When you go with set A, it is an countable and finite set. We can count the values, that is 1, 3, 5, 7, and these are limited, so it is an finite set. Set B, when you look into set B, these are countable and infinite. Set B is countable and there are infinite number of elements, so it is called as an infinite set. Now here in this case, C is an uncountable and finite set. Uncountable and finite set. That is, the values are limited between these two. The values are limited between these two and they are uncountable. Uncountable in the sense we cannot specify what value is going to lie in between these two. That is 0.5 to 8.5. We can have all numbers 1, 2, 3, 4, 5, 6, 7, 8 or 0.5, 1, 1.5 in that way up to 8.5 or 0.01, 0.02 in that way to the end value of 8.85. So we cannot specify the value. So it is an uncountable set and finite set. And next D. D is an countable and finite set. D is countable and finite set. Similarly, E is also countable and finite set. You have got limited number of elements and they are countable. Now when you go with F, here set F is countable and infinite. Set F is countable and infinite. Why? Because we are specifying F values in between these two, -5 to 12. -5 to 12. Here in this case, fractions are there, so it is uncountable. Here natural numbers are there, so they are countable. That is -5 to 12. Sorry, we have got -5 to 12, so they are countable and infinite. Set D is not an empty set. Set D is not an empty, since it has got two elements 0 and 0. Set D is not an empty set. Now A is a subset of B. A is a subset of B in the sense all the elements of A are lying in B. All the elements of A are lying in B. So we call it as an A is a subset of B. Now A is a subset of F. A is a subset of F. So all these values 1, 3, 5, 7 are also in between these things. So A is a subset of F. Similarly, A is a subset of C. A is a subset of C. So these values lie in between these two. C is a subset of F. C is a subset of F. Yes, 0.5 to 8.5. All these values are going to lie in between these two. Next, D is a subset of F. D is a subset of F. Yes, 0 is where lying in between -5 and 12. So D is a subset of F. E is a subset of B. E is a subset of B. Yes, all these are even numbers starting from 2 to 14 are also natural numbers, so they lie in between these. So E is a subset of B. Set operations. What are all the operations we can perform on sets? We can perform 3 to 4 operations. One is you've got n number of operations, but the thing is here our interest is with union, intersection, and negation. So here in this case, the union of two sets is the set containing all of the elements from both of those sets. Written A union B and defined A union B equals X such that X belongs to A as well as X belongs to B. Example 1, 2, 3, 4 union 3, 4, 5, 6 will give it as 1, 2, 3, 4, 5, 6. Since 3 and 4 are repeated, we can write it only once. 1, 2, 3, 4, 5, and 6. Here, if we have n number of sets, n number of sets, if you perform how to perform union operation, so we'll represent the union operation as union k equals 1 to n ak, where k is varying from 1 to n, and between all these sets the operation is union. The union of all is given as with this particular equation. Similarly, intersection. The intersection of two sets is the set containing elements which are in both of these sets. So written, that is common elements between the sets. Written A intersection B and defined A intersection B equals X such that X belongs to A as well as X belongs to B. Example 1, 2, 3, 4 intersection 3, 4, 5, 6. Common element between these two is 3, 4. So we write it as 3, 4. if A1, A2, A3, and so on up to is a sequence of events, we denote intersection in this way. K equals 1 to n, that is A1 intersection A2 and so on intersection AN. This is the expression what we use for performing intersection operation between n number of sets. Now the difference between two sets. The difference between the two sets is the set of values in one but not the other. That is A minus B equals X such that X belongs to A and X does not belong to B. The values what we see in case of A minus B set are the values which are in set A, not in set B. Example 1, 2, 3, 4, minus 3, 4, 5, 6. If you perform this operation, common element, the elements which are present in B and which are present in A, common between these two are eliminated, and the remaining elements which are present in the first set are given as a result. That is 1, 2, 3, 4 minus 3, 4, 5, 6. Like your result will be 1, 2, not 5, 6. 5, 6 you are not going to include. Now two sets A and B are equal if all the elements in A are present in B and all the elements in B are present in A. And you've got more set operations to go. These are the set operations which are not that much required right now for your probability theory, but you can see these things. Involution property, that is A complement whole complement is A, that is negation of A is A. Commutative property, in case of commutative property, A union B equals B union A intersection B equals B intersection A. Intersection and union satisfies commutative property. Similarly, intersection and union satisfies associativity, directivity, distributivity. Idempotence, A union A equals A intersection A equals A union A equals A, and A intersection A equals A. Absorption, A union A intersection B equals A intersection A union B equals A. Absorption by X and L, that is this is an set and this is an empty. A union X equals X. A intersection phi is phi, that is phi is a null set which does not contain any elements. When you perform intersection operation, you'll have phi. Now when you perform A union phi, which is A intersection X is A. Here we can have an example for analysis. Now if you see X is an universal set, think universal set, you've got 1, 2, 3, 4, 5, and 6. And A is a set which is having the elements 2, 4, and 6. Now once when you perform A union X operation, that is performing union operation between A and X, when you perform union operation, you'll have all the elements which are present in X as well as A. Here in this case, when you see 1, 2, 3, 4, 5, 6 are in X and 2, 4, 6 are in A. These 2, 4, 6 are also present in X. So finally, when you perform this operation, you come across the same values which are present in X. And when you perform intersection operation with empty set, A intersection phi, you are going to have the values which are present in A itself. So here intersection, that is you are checking the common element. So phi is an empty set. This phi is an empty set. So when you look into these two, there is no common element. There is no common element in the sense the common elements are empty space. So it's a null set. Similarly, when you perform A union phi, when you perform union operation of these two, all the elements which are present in A and null set must be there. So when you perform union operation with a null set, you'll have the same set. Similarly, A intersection X, when you perform A intersection X, X is the one which we call it as an universal set which contains all the values. Now here when you perform intersection operation between these two, common elements are to be connected. So here you are going to get the result as A. You are going to result as A. Now when you see Next, A intersection A complement. When you perform A intersection A complement, you are going to have your
This conference will now be recorded.
now when you look into law of contradiction, you'll have A intersection A complement, which is 5. That is, A is a set which is having the values. A is a set which is having the values in the sense, I can give this in this way. When you consider a set, this is X and this is A and this is A. Now when you look into this complement of A, this, the part which is other than A is A complement. A complement. Now when you perform intersection operation between these two, there is no common element between these two, so you're going to get empty set. Now when you perform union operation, A complement and added with this A, you'll have X, that is given here, right? Similarly, you can have De Morgan's laws explained. In case of De Morgan's laws, A intersection B whole complement equals A complement union B complement, and A union B whole complement equals A complement intersection B complement. Now we'll go with the concept of probability. Till now we have seen set theory. Now using those concepts, we'll try to analyze probability theory. And here in this case, the probability theory is the mathematics of randomness. That is, you cannot expect what outcome you are going to have with your experiment. That is, what do you mean by randomness? That we need to have an idea. What is randomness? Now, when you see, this is a deep question that we cannot attempt to answer without invoking the disciplines of philosophy, psychology, mathematical complexity theory, and quantum physics. And still there would most likely to be complexity satisfactory answer. Complete, you don't have any, no complete satisfactory answer will be given with these all these things. It is less than 50% of the required answer. So for our purpose, an informal definition of randomness as what happens in a situation where we cannot predict the outcome with certainty is sufficient. Now, if there is no certainty in the answer, then in that case, we call it as an lack of information. In many cases, this might simply mean lack of information. You don't have any information. Clear? So in order to have this, for example, in order to explain this thing, for example, if we flip a coin, we might think of the outcome as random. It will be either head or tail, but we cannot say which head or tail. We cannot predict that we are going to have head or tail. So if the coin is fair, we believe that both outcomes are equally likely. If the coin is not fair, it is unfair, then in that case, you cannot predict the outcome of your experiment. Then in that case, we need to see all these things. We need to consider all these parameters in order to have your fairness in the coin. That is, the force from the fingers at the flip, weight and shape of the coin, material and shape of the table surface, and several other parameters. If you look into all these factors and flip a coin, there is a possibility of getting a equal outcome. That is, either it may 50% heads and 50% tails. But if you are not going to consider all these things, then in that case, the coin will be unfair. Next question is, what is probability? We have seen randomness. We'll have a question, what is probability? There are two main interpretations of probability, one that could be termed objective and the other to be subjective. That is, if it is an objective case, probability as an limit of relative frequencies. That is, limit of relative frequencies. And if it is subjective, degree of belief. That means by looking into the experiment, we can say here in this case, mathematically we can classify. Now here we'll see the first objective concept, relative frequency. We consider n repetitions of an experiment, and if Sn of those gave our outcome, then the relative frequency would be Fn, which is Sn by n. That is probable outcomes, that is whatever the required outcome is there, the number of required outcomes by total number of repetitions, that is Sn by n. Now we'll take an example. When you take an example of flipping a coin, if you are flipping a coin 100 times, this is a computer simulated result. Here in this case, getting 50%, that is 50% of heads and tails in a coin are there. Half probability of getting a head is 50%, probability of getting a tail is 50%. Here in this case, at the starting, you have got the probability to be less than half, but as the time passed, as the number of turns increased, the probability of getting heads or tails is equally probable. And probability as a degree of belief, this is your second concept, subjective, is not easily quantified but has obvious intuitive appeal. That is, for example, in a weather forecast, you will often hear statements like there is a 30% chance of rain tomorrow, only 30% chance. That is depending upon the previous data what you have. We give only 30% assurance that tomorrow you are going to have a rain, or today we are going to have a rain, but we cannot give the complete thing. This 30% is a meteorologist's measure of the chance of a rain. This is the data, previous data. From the previous data, they have given that this year, this day, we are going to have a rain of chance of rain to be 30%. That is 0.3 probability is present over here. Now, there is still a connection to the relative frequency approach. We can imagine a sequence of days with similar weather conditions, same time of year, and so on, and that is roughly 30% of the cases. It rains the following day. That is, we'll see previous years the same day. Is there any rain on this particular day? Based on those data, you are going to roughly estimate that there will be a 30% of chance to have a rain. Now, the degree of belief approach becomes less clear for statements such as there is life on other planets. Obviously, there are statements that are either true or false, but we do not know which, and it is not unreasonable to use probabilities to express how strongly we believe in their truth. That is, there is a life on the planet, on other planets. This is only a contradictory statement. Now, how then do we actually define probability? So, subjective or objective analysis of probability is not proper. So, we define mathematically the definition of probability. Instead of trying to use any of these interpretations, we will state a strict mathematical definition of probability. Probability theory is a mathematical theory to describe and analyze situations where randomness or uncertainty are present. Randomness and uncertainty are present. Any specific such situation will be referred to as a random experiment. Example, flipping a coin or rolling a die. When you flip a coin, you may get head or you may get a tail. Or when you roll a die, you may get any one of the 6 outcomes, 1, 2, 3, 4, 5, and 6. After the experiment is over, we call the results an outcome. For a given experiment, there is a set of possible outcomes. For a given experiment, there is a set of possible outcomes. The set of all possible outcomes in a random experiment is called the sample space. Sample space denoted with S. Now, we'll see 2 examples. Rolling a die and observe the number. When you roll a die and observe the number, here in this case, we can get the numbers from 1 through 6. That is, hence the sample space is going to have numbers 1, 2, 3, 4, 5, and 6. We have these numbers. This is a sample space which is having the outcomes to be 1, 2, 3, 4, 5, and 6. Similarly, roll a die repeatedly and count the number of rolls it takes until the first 6 appears. Now here in this case, we cannot specify when the first 6 is going to appear. That is, in the first instance itself, 6 may appear, or in the second instant it may appear, or in the third instant it may appear, or in the fourth instant it may appear. We cannot specify in which instant you are going to get a 6. So getting a 6 is an infinite set. So 1, 2, 3, 4, 5, 6, your count of experiments goes on increasing when you roll a die and expecting for a 6 to appear. Now, one more example. Flip a coin twice and observe the sequence of heads and tails. When you flip a coin twice, there is a possibility of getting head first and head next. Similarly, head first and tail next. Tail first and head, and similarly you may get both tails also. So the set contains these 4 combinations. The set is going to have these 4 combinations. You may see these 4 combinations when you toss a coin twice. S equals HH, HT, TH, and TT. Now, throw a dart at a random on a dartboard of radius R. So you have got a board which is in the circular form, having a radius small r. Now, the probability of hitting in this area, and when you see, your set is going to have these things. That is the circle which is represented over here. When we represent this in coordinate system, here x square plus y square is less than or equal to r square. This is the set what you are going to see here. S is a set of x comma y where x square plus y square is less than or equal to r square. This is the condition what these 2 points are going to satisfy. When you represent the circle on your coordinate system, if I represent this in this way, your S is going to have a points located around this, which is represented with x and y coordinates, and these coordinates must satisfy this particular condition. The radius of this is going to be r. Now, once when it satisfies this, you are going to have your sample space to have x comma y such that your x square plus y square is less than or equal to r square. Now, first, we'll define few terms in sample space. A set of all possible outcomes in a random experiment is called the sample space, denoted by S. We have seen this in the previous slide also, but the thing is, we'll see in detail now. It is denoted with capital S. Now, this sample space is of 3 types. Next is first, discrete and finite sample space. Discrete and finite sample space. You've got finite number of elements and they are discrete. 1, 2, 3, 4, 5, and 6. Similarly, about discrete and infinite sample space. For this, choosing randomly a positive number. S equals 1, 2, 3, 4, 5, so on. And similarly, continuous sample space. Obtaining a number by spinning the pointer on a wheel. So 0 less than S less than or equal to 12. 0 to 12 numbers are pointed on that. And between these two, you're supposed to spin your pointer. So that depends upon the spin. Any value between 0 to 12 can be shown on that. This is a continuous sample space. Now, events. An event is defined as the subset of the sample space. An event is defined as the subset of a sample space. Here in this case, you've got discrete and finite event. Types of events, you've got all the 3 similar to your sample space. Discrete and finite event, drawing a particular card in a deck. You've got 52 cards in a deck. From the deck, you can pick anything, and that is a finite event, and it is discrete. Now, discrete and infinite event, choosing randomly a positive number or choosing an odd number, it's an infinite event. And continuous event, yes, the value between 6 and 12, it's a continuous event. Now, for defining your probability, I've got few properties to be satisfied. That is, we call it as an axioms of probability. Now, when you look into this, a probability measure is a function P which assigns to event A as P of A, satisfying this condition. First condition is probability of an event A. An event A should have the values between 0 and 1. 0 less than or equal to P of A less than or equal to 1. That the values should not be less than 0 and not greater than 1. The probability what you obtain should have a value in between 0 and 1. Next, the probability of a certain event or an universal set is 1. A certain event, S is known as a certain event. Here in this case, the probability of a certain event is 1. And the probability of an empty set. If A1, A2 and so on is a sequence of pairwise disjoint events, that is, if I is not equal to J, then A of I intersection A of J is 5. That is, these are all pairwise disjoint events. Disjoint events in the sense there are no common elements between all these things. When there are no common elements in the sense A1 is an set odd number obtained when you are rolling a die. So you'll have 1, 3 and 5. And A2 is an event which is going to have even numbers 2, 4 and 6. Now when you perform operation, intersection operation between the two sets which are not having common elements, then in that case you will have empty set on. Then P of, where you can mathematically write the same expression for infinite number of disjoint events using this relation. Let P be a probability measure, then P of phi is 0. That is what I've given. Phi is an impossible event. For an impossible event, the probability of a null set is 0. You don't have any probability for a null set. If A1, A2 are pairwise disjoint events, then P of A and give same statement. If A and B are disjoint, then P of A union B is equals to P of A plus P of B. If A and B are disjoint, then P of A union B equals P of A plus P of B. Generally speaking, here P of A union B plus P of A intersection B will be equal to P of A comma, this will be here. Now here in this case, since these two are disjoint sets, your P of A intersection B will be 0. So in that case, your P of A union B will be equal to P of A plus P of B. Now in this case, let P be the probability measure on a sample space S, and let A and B are the B events. Then P of A complement will be equal to 1 minus P of A. That is, probability of A complement of a set will be equal to 1 minus P of A. And P of A union B equals P of A plus P of B minus P of A intersection. Now here in this case, if A and B are disjoint or mutually exclusive, in that case, this factor will be equal to 0. That is what we have seen in your previous slide. P of A union B equals P of A plus P of B. Next, if A is a subset of B, then P of A is less than or equal to P of B. A is a subset of B, then probability of A will be less than or equal to probability of B. Now, let P of A comma B comma C are 3 events, then P of A union B union C equals P of A plus P of B plus P of C minus P of A intersection B minus P of A intersection C minus P of B intersection C plus P of A intersection B intersection C. This is the expression we use for calculating the union of all the 3 events probability of all the union of 3 events. This is the thing. We'll see individual probabilities, intersection of 2 and intersection of all the 3, and we use this relation to have your probability. Similarly, we can have it for n number of events. Now we'll see this particular experiment. Choosing a number at random from the numbers 1 to 100, what is the probability that the chosen number is divisible by either 2, 3 or 5? Either 2, 3 or 5. So you're supposed to calculate the values. Now here in this case, the probability of getting A2, that is, here in this case we are going to calculate probability of 2 union 3 union 5. We need to calculate these things. Probability of getting 2 union, getting 3 union, getting 5. That is, when we choose a random number between 1 and 100, the number obtained is divisible by 2, 3 and 5 as well. It has to be divided by all the 3. This we are supposed to calculate. Now for that, first we'll try to calculate the number obtained is divisible by 2 or not. So now here in this case, from 1 to 100, from a set of 1 to 100, the numbers which are divisible by 2 are 2, 4, 6 and so on up to 100. This contains 50 elements. This contains 50 elements. This set is going to have 50 elements. The total number of elements are 100. So 50 divided by 100 will be 0.5. 50 divided by 100 gives half, which is equals to 0.5. Now here in this case, the number which is divisible by 3, that is 3. Here in this case, from 1 to 100, the numbers are 33.33. 1/3 of the numbers are divisible by 3. And when you go for 5, the numbers which are divisible by 5 will be 20. That is 20 by 100. It gives 20 by 100. That is going to be 0.2. That is going to be 0.2. And similarly, we calculate P of 8, the number divisible by 2 and 3. That is probability of A6. That is in the case 0.16. That is 0.16. The numbers which are common between elements which are divisible by 2 and 3. The numbers which are divisible by 2 and 3 as well will be 16 numbers, and the numbers which are divisible by 2 and 5 both are 10 numbers. 2 and 5 both are 10 numbers. That is 10, 20, 30, 40, 50, 60, 70, 80, 90 and 100. All these things are divisible by 2 and 5, so it is 0.1. Similarly, when you go for dividing the obtained number with 3 and 5, both the values will be 6. That is, the numbers which are divisible by 3 as well as 5 are 15, 30, 45, 60, 75 and 90. We have got 6 numbers which are divisible by 15. So these are the probabilities of these things. And similarly, we'll go for obtaining the numbers which are divisible by all the 3, A2, 3 and 5. So you'll have 3 numbers, 30, 60 and 90. So the value is 0.03. Now, in order to obtain what is the probability that the chosen number is divisible by either 2, 3 or 5? That is any one of these things. P of A2 union A3 union A5 is equals to P of A2 plus P of A3 plus P of A5 minus P of A2 intersection A3 minus P of A2 intersection A5 minus P of A3 intersection A5 plus P of A2 intersection A3 intersection A5. That is 0.5 plus 0.33 plus 0.2 minus 0.16 minus 0.1 minus 0.06 plus 0.03. Totally you are going to get 0.74. So the probability of getting a number which is divisible by either 3, 2 and 5 is 0.74. And you have got, when you have got n number of events, then in that case calculating the union operation with probability of union of all these events will be given by this one. First you can see here summation of k equals 1 to n p of ak. You need to add the probabilities of all the events minus probabilities of intersection of two events, and next plus probabilities of intersection of three events, next minus probabilities of intersection of four events. When there comes an intersection operation with even number of events, you'll have a minus sign in front of them, and when there are odd number of events performing intersection operation, you'll have positive symbol. By doing all these things, you'll get the union of all these events. Now, the classical definition of probability. In a finite sample space with uniform probability distribution, P of A equals favorable outcomes by possible outcomes. Here in this case, we'll see an example. Performing the experiment of flipping a fair coin twice and counting the number of heads. That is, you are going to perform experiment flipping a fair coin twice and counting the number of heads. Now, when you do these things, we can take sample space. It has head, 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 tail, tail, head, and tail, tail. Now, the probability of no heads is 1/4. Now, here in this case, see, no head case is you have got T and T. So, the favorable outcomes are 1 and the total outcomes are 4. So, 1/4. So, probability of one head. Probability of one head is 1 HT and TH. So the probable favorable events are 2 and the total is 4. So 2/4, you are going to get 1/2. Probability of two heads cases is only 1. So the number of favorable outcomes is 1 by total number of outcomes is 4. So it is 1/4. Now, when we go for a next example, rolling a fair die 3 times, what is the probability that all numbers are the same? If you roll a fair die 3 times, what is the probability that all the numbers are the same? Now you are going to roll the numbers thrice. So first you'll get all ones, next 1, 2, 2, 1, 3, 3, 1, 4, 4, 1, 5, 5, 1, 6, 6, and you can have the combination. You may have 1, 1, 2, 1, 1, 3, 1, 1, 4. In that way, you can define this thing. And similarly, you can start with this 2, 1, 1, 2, 2, 2, 2, 3, 3, 2, 4, 4, and this goes on. And similarly, 3, 1, 1, 3, 2, 2, 3, 3, 3. In that way, it goes on. Here you'll have 6, 1, 1, 6, 2, 2, 6, 3, 3, 6, 4, 4, 6, 5, 5, 6, 6, 6, and so on. In between of this, you'll have 4, 4, 4, and 5, 5, 5. Now here see, what is the probability that all numbers are same? These are the cases which are having equal number of shows. Now, when you look into this, experiment of getting a value. This is the thing. Favorable outcomes are 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, and 6, 6, 6. So 6 possible cases are there, and the number of possible outcomes are 216. Placing 1 and changing these two, you'll have 36 combinations. Similarly, 2, 36, 6 into 36, you'll have 216 possible outcomes. In that, the favorable outcomes are only 6. So 6 by 216, you get 1 by 36. Now, next example. Perform the experiment of randomly chosen family with 3 children. What is the probability that they have exactly 1 dot? So this is the case of getting only a head when you are tossing a coin twice, similar type of this thing. Here in this case, these are the cases. You can see you've got 3 children. You'll have 8 possible combinations: BBB, BBG, BGB, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Now here in this case, what he has asked is, what is the probability that they have exactly 1 daughter? So in this case, one girl child, you're going to one girl child combination we need to see. When we see the favorable outcomes, when you go for one girl child, you see 1, 2, and 3. And the remaining places, either you have got 0 girls or 2 girls or 3 girls. So the favorable outcomes are 1, 2, and 3. So the probability is 3 by total number of combinations are 8. So 3 by 8. Now we'll stop with this and we'll continue in your next lecture.